Hi everyone. Today I'm going to talk about an interesting topic related to zero knowledge proof. And through this topic, I want to introduce a new set of tools so that you may apply in your projects. And this tool may also uncover a new set of features for your future DApps. And the talk today can be divided into three sections. In the first section, I'll talk about the concept of zero-knowledge proof and zk-SNARK, which is one of the most commonly used protocols to implement zero-knowledge proof. And in the second section, we'll go through the steps to build a ZKD app. In the last section, we'll discuss about Tornado Cash, which is a practical example demonstrating the application of zk-SNARK to blockchain dApps. Now we'll come with the first section. So what is zero-knowledge proof? Zero-knowledge proof is a way of proving the validity of a statement without revealing the statement itself. For example, you can prove that you know the solution to an equation without revealing it, or you can prove that you know a password to access a particular website without sharing it with others. Or you can prove that you are old enough to hire a car without disclosing your actual age or identity. These examples demonstrate the concept of zero-knowledge proof and which can enforce honest behavior while also maintaining privacy. Furthermore, there are two types of zero-knowledge proof: interactive and non-interactive. The first one requires repetitive interactions between the prover and the verifier, while the second one does not. And in the scope of this presentation, we'll primarily focus on non-interactive zero-knowledge proof. And this is some of the examples about applying zero-knowledge proof in blockchain the app. And one common term that many of you may have heard is zk rollups. It is a blockchain scalability solution that bundles transactions into a batch that are executed off-chain, and by checking the generated validity proof, the changes made by these transactions can be applied quickly without re-executing them on the main chain. The second example here is Tornado Cash. This is a DeFi protocol that allows users to make anonymous transactions on the Ethereum blockchain. And this example will be discussed in more detail in the last section. Moreover, zero-knowledge proof can also be applied in some other problems such as proof of membership or anonymous voting. In order to implement zero-knowledge proof in our dApps like Tornado Cash, we can use a protocol called zk-SNARK. zk-SNARK is a non-interactive ZKB protocol that allows proving computational statements represented in the form of an arithmetic circuit. Specifically, it means that we must convert our problem into a series of arithmetic constraints using the circum language. And it's important to note that only quadratic expressions are allowed to be included in our constraints. Quadratic expression is an expression in the form of a star b plus c, where a, b, and c are linear expressions. To generate the proof, the prover here has to fill the circuit signals with a set of public and private values so that all of the constraints in our circuit is satisfied. And this set of signals are called witnessed. To gain a deeper understanding of this process, let's move on to the next section. In this section, we'll try to analyze the steps to build a ZK app using zk-snark. The first thing we want to talk about is the trusted setup process. From here, we'll use Snark.js, which is a JavaScript implementation of zk-snark, along with the cross-sitting proving scheme. And another scheme that can be used in Plon is Plonk, which has a larger proof size compared to cross-sitting. However, the cross-sitting scheme requires two phases of trusted setup, and in each phase, multiple parties need to participate and commit random values to produce the trusted setup data. And as a developer, we only need to do the phase 2 ceremony that generates a ZK file for each circuit using the available power-up file from phase 1. This file can be downloaded publicly from the internet, and after obtaining the ZK file from phase 2, can use this file to generate the proving and verification keys. And the overall flow of using Snark.js can be illustrated in this figure. In the first step, we need to convert our problem into the circuit and compile it using the Circum compiler. Two files will be generated. The first one is the WebAssembly file to run the circuit and generate the proof. And the second R1CS file contains all of the constraints in our circuit that will be used to generate the ZK file during the phase 2 ceremony and the verifier solidity contract. The public JSON file here contains the values of our public signals, while the proof of JSON file is used to prove that we know the values for the corresponding private signals. Submitting these values as call data to the verify proof function in the verifier contract can check for the validity of the proof without revealing the actual value of our private signal. The proof generation process occurs within the prover browser, which requires the Snark.js library to be imported along with the circuit WebAssembly file and the ZK file. Once the proof is constructed, the prover can include it as a parameter in the transaction to our DApp contract. To validate the proof, the DApp contract will need to call the verify proof function in the verifier contract. Now in the last section, we'll come with a practical example, Tornado Cache, and through this section, we'll analyze how Tornado Cache works and how zk-snark can be applied to achieve transaction privacy. Tornado Cache can be seen as a coin mixer, where multiple users deposit their coins into the contract. The contract then mixes this coin and allows recipients to withdraw the corresponding amount. However, we need a way to hide the connection between the depositor and the withdrawer. But how can you prove that you have deposited your coin into the contract without disclosing your account? This is where a zero-knowledge proof comes into play. Another thing to note is that the deposit and withdrawal amount can potentially reveal your identity. For example, if you're the only person who deposits and then withdraw one ETA in the contract, so anyone can use this evidence to link the depositor and the withdrawer. So the contract should only accept the same amount for all deposits and withdrawals. Before depositing our coins into the contract, we need to generate a secret and a nullifier value. Combine these two values together through the Peterson hash function, we'll get a new value called commitment. The commitment here will be stored as a leaf in the Merkle tree of the tornado contract, and each deposit will have a corresponding commitment. And the current depth of the Merkle tree is set to 20, so the maximum of deposits would be 2 power 20. The hash of the nullifier value would then be used in the withdraw function to avoid the post-spending problem. And to withdraw our coins, we need to prove that the Merkle tree contains our commitment. And a simple way to prove that is using the Merkle proof. But using the Merkle proof, we leak the content of the leaf node, which is our commitment. So the problem becomes proving that you have the valid Merkle proof for the Merkle tree without disclosing it. And to overcome this problem, we'll use the Merkle proof as a private input to the zk-SNARK circuit. In general, the circuit for withdrawal verification should contain the following inputs: the root value, which is the Merkle tree root hash after the coin is deposited. The nullifier hash is the hash of our previous nullifier. This value is used to avoid double spending. And some more variables can be included in our circuit, such as recipient, relayer, fee, and refund. The private inputs to our circuit are the nullifier, secret, path elements, and path indices. The last two arrays represent the Merkle proof for our commitment. And this is the STIR-COM code for our withdrawal circuit. These input signals have been explained in the previous slide, and the code here is just to check the validity of our Merkle proof with the root hash. To withdraw our coins, we need to submit our zk-SNARK proof along with public values such as root, nullifier hash, recipients, etc. The withdraw function in the Tornado Cash contract will check the nullifier hash first to prevent proof reuse. After that, the zk-SNARK proof will be validated using the verified contract generated from the circuit. The root value will also be checked against the recorded root history. This means our proof can be used for the next 30 deposits. After 30 deposits, our proof will be considered expired, and we'll need to generate our proof again using the updated root. To enhance the system privacy, the Tornado Relayer is added as an additional security layer. In the Ethereum blockchain, an account needs to be funded with ETH as gas in order to make the withdrawal transaction. However, the funding process may leak the identity of the depositor. So the tornado relayer will be used to make the withdrawal transaction on behalf of the recipient, and it will take a small fee. We only need to provide it with the proof, recipient, and other public inputs. And this is the end of the talk today. I hope that my presentation can give you a clear understanding about the application of zero knowledge proof and enabling you to discover new features for your dApps. And if you have questions or concerns regarding the security of your dApp projects, feel free to contact us via email or submit our audit request on our website. We're here to assist you. Thank you.